and everything would work, except that the DC levels at the bases of those two transistors would be different because of the junction drops, and the limiter circuit wouldn't work. Now let's tie them together and put a couple of diodes to make the DC levels come out right, and see how that'll work. Let's begin with the cathode of CR4323, and let's call that reference. All right, we're up a junction through CR4323, down a junction to the emitter of Q4325. So that's reference right there. Let's drop down to the cathode of CR4333. And we'd like to have that at the same voltage, wouldn't we? All right, we're up a junction through that diode, up another junction through Q4335. So we're up two junctions now. All right, let's drop down then through CR4344 and CR4346, and we're back to reference again, you see, at the emitter of Q4325. So the two diodes allow us to effectively tie those two emitters together and still provide the DC levels necessary to the limiting circuit. Well, the presence of the diodes, however, interfere with normal standing current flow. In other words, electrons can flow through Q4335, but we're going backwards through those two offset diodes. So we need another current path, and that's the purpose of our 4342 to plus 15 volts. There's another one to provide standing current for the emitter of Q4325. That's our 4340 to ground. Now, as we adjust the thermal balance resistor, what we're trying to do is to change the supply voltage at the top of the thermal balance resistors for Q4321 and Q4331. Let's see how that's accomplished. As we adjust the control, that voltage is felt at the emitter of the voltage setting emitter follower, Q4346, which then effectively raises the emitters of both Q4325 and 4335, both going in the same direction, you see. Now through feedback action, that'll raise the bases of those two transistors, which in turn will lift the top of thermal balance resistors R4321 and R4331. Now, right between the base and emitter of Q4346 is another protective diode, CR4348, and that's protection in case Q4335 is pulled out of the socket. That emitter, you see, would go towards a plus 15 volts, lifting through CR4344, lift the emitter of Q4346 above its base far enough to cause base emitter breakdown. Now, right across those two offset diodes is C4342. Now, that provides additional current at the faster sweep speeds for both Q4325 and Q4335. In fact, that provides a complete circulating path of high-frequency currents. Now let's begin with the right deflection plate. And we're talking about current to charge and discharge the deflection plate capacitance. All right, let's start at that point, go over to the left through Q4395, that's the fast path transistor, to the left through C4335, through Q4335, now through C4342, up to the emitter of Q4325 through that transistor, to the right through C4325. Now, since we're talking about a fast path, we'll bypass Q4356, go up through C4354 through Q4371 to the left deflection plate. So we have a complete circulating path for high-frequency currents. Now, I promised to tell you about the mod to this circuit, which allows the limiter circuit to work properly. Now, if you'll begin with the input push-pull amplifier, and the collector load resistors. R4323 went to 549 ohms. Same value for R4333, of course. The centering control went to 100 ohms. Now down in the emitter supply, in series with the gain control, R4311, 82.5 ohms. Off to the left there, the collector load for Q4304 went to 100 ohms. Now off to the right there by the thermal balance control, just above it, R4344 went to 825 ohms. Then up and to the right, the bias resistors for Q4381, R4382 went to 2.21K, R4384 to 2.32K. Now the bias resistors down below by Q4390, of course, went to the same values. Now I don't have the serial number break, but it was supposed to have gone into the line about the middle of May 1973. The next schematic is output signals. Let's pull out schematic 7. Now there we have the outputs which appear on the rear panel of the scope. The vertical signal out, plus sawtooth out, and plus gate. Now the source of the vertical signal out signal is selected by the B trigger source switch. It has a value of 0.5 volts per division into 1 meg and 25 millivolts per division into 50 ohms. The source impedance, by the way, for all of these output lines is 950 ohms. So there's a ratio of 20 to 1, whether open circuited or into 50 ohms. The sawtooth out signal is selected by a sweep selector switch on the side of the signal's output board. The selection there is made for either A sweep or B sweep. In either case, the output is a positive going ramp, 10 volts into 1 meg, 0.5 volts into 50 ohms. The plus gate out is also selected by a switch on the side of the signal output board. The switch is labeled gate selector. It's either A gate, B gate, or delayed gate. In any case, the gate out signal is 10 volts into 1 meg or 0.5 volts into 50 ohms. Well, let's look first at the vertical signal amplifier. The source of signal comes from pull-out schematic 4, so let's turn over there for the moment. Now at the bottom of the page, the output from the B trigger selector takes off into amplifier Q2434 and Q2436. The signal line then, push-pull, goes to the signal's out board. Notice that the line is reverse terminated in 50 ohms. All right, back over to schematic 7 up in the upper left-hand corner. The line is terminated now in 50 ohms per side again with R3302. The signal current is 0.5 mils per division. Since we're double terminated, that means that the signal at the bases of these two transistors would be 12.5 millivolts per division per side. Q3306 and Q3308 is a push-pull to single-ended amplifier. Signal current being taken from the collector of Q3308 to pass through grounded base amplifier Q3315. Now in the collectors of Q3306 and Q3308 are thermal balance resistors, R3312 and R3315, with a conventional bypass. Now the collector supply for Q3306 and Q3308 are the emitters of Q3312 and Q3315. Those two transistors temperature compensate one another to provide identical loads for the push-pull to single-ended amplifier, thereby maintaining thermal balance. The bases of Q3312 and Q3315, by the way, set at about 9 volts. Notice the emitter peaking in between the emitters of Q3306 and Q3308. There's C3309, and then the RC network C3310 and R3310. The collector load for Q3315, through which the signal current flows, is a parallel combination of R3317 and R3318. 7 and equivalent there is about 850 ohms. Now that resistance and R3319 forms the 950 ohm source impedance that we mentioned earlier. Now the output is 0.5 volts per division into 1 meg. However, if you load it in 50 ohms, then that 50 ohm resistance and the 950 ohm source impedance form a 20-to-1 attenuator, and the output is 25 millivolts per division. Now, since the vertical signal out jack is a rear panel connection, somebody could quite easily connect a large voltage to it, which could damage our circuits. So we've protected the circuits with 2 diodes. In the negative excursion, CR3317 limits at a minus 15 volts. In the positive excursion, CR3315 disconnects. Well, let's look at the plus sawtooth out. Now the choice, as I said earlier, is made by the sweep selector switch, and the source of signal is the A sweep out ramp from the A time-based generator. It's a negative going 5-volt ramp and passes through a 2.49K resistor before it enters this page. You may want to pencil that in the margin. The B sweep ramp, also negative, going 5 volts in amplitude, also passes through a 2.5K resistor. The amplifier is an operational amp composed of, well, all 3 transistors in this circuit. RF is R3328. RI would be whichever of those 2.5K resistors we've selected with the sweep selector switch, in series with R3321. Now, the purpose of R3321 is to allow some signal voltage to appear for test purposes at the 2 input jacks here, J3307 and J3308. See, since the base of Q3321 is the null point in the operational amplifier, were it not for R3321, we wouldn't be able to measure any signal voltage at those input jacks. Q3321 and Q3323 is a common emitter stage. With the base of the latter transistor tied to ground, we're assured that the base of Q3321 will be at precisely 0 volts. The 2 transistors temperature compensate one another. The collector load for Q3323, just 240 ohm value of R3325, directly coupled into the base of Q3330. And that's the output from the circuit, and also driving the feedback resistor. C3320 and R3330 provide some negative feedback within the loop to suppress a ringing that was occurring at the end of retrace. The 950 ohm source impedance is R3334 in series with the output impedance from the operational amplifier. Output voltage, as I said earlier, 10 volts, positive going into 1 meg, 0.5 volts into 50 ohms. Now, protection is afforded by a couple of diodes in the negative excursion, 3333 clamps at a minus 15 volts, and the positive excursion, we forward bias the base collector junction of Q3330, lift the base of that transistor, and at 15 volts, CR3326 limits to protect Q3323. Well, the next circuit is the plus gate out circuit. As I said earlier, we have a choice of 3 gates. First, the A gate from the A time base. Now that's a positive going 5 volt gate. And in series with the line coming onto this page is 1.3K. The next one, the B gate from the B time base. Again, a 5 volt positive going gate with 1.3K in series. The delayed gate comes from the A time base only, from pin B9 in the interface. It's a negative going gate, 5 volts in amplitude, and again a 1.3K resistor in series. Well, let's look at the A gate input first. We go into divider R3340 and R3341, which offsets that line to about a minus 2 volts. Then, considering the 1.3K resistor in series, attenuates that signal to a little less than 500 millivolts. All right, that signal then goes into common emitter amplifier Q3351 and Q3353, and we're going to just switch currents in that amplifier. Now, as I said earlier, the base of Q3351 sets at a minus 2 volts. We're down a junction to the emitter of that transistor. So the current flowing through R3352 is 12.4 mils. Now when we transfer that current through Q3353, then we get a 3.7 volt drop across R3358, bringing that level down to 11.3 volts. Now you may want to make a note of that. Now, off to the right there, the base of Q3361 sets at almost exactly 11 volts. So with the emitter at 11.3 volts, then that transistor is turned off. Its collector is at ground, pulled down by R3363, and that's the negative excursion of the plus gate. Now back to the common emitter amplifier. When Q3351 turns on, diverts the current in that direction, then the collector of Q3353 goes up to plus 15 volts. That lifts the emitter of Q3361. It saturates at the base level, 11 volts. All right, let's take that level at the collector of Q3361. We're down a junction through CR3363, and that is the positive excursion of 10 volts at the plus gate out jack. So all of these transistors are merely switches in this circuit. CR3361 temperature compensates the base emitter junction of Q3361. Over at the common emitter amplifier, notice the thermal balance resistors are R3354, and then everything in the collector of Q3353. Now, the reason they attenuated the input signal was to keep the switching voltages as low as possible, but with that low a signal fed into this common emitter amplifier, then it was necessary to temperature compensate it in order to switch the currents with this relatively low gate signal. Okay, the delayed gate, negative going as we said earlier, feeds into the base of Q3353. There we get polarity reversal to provide the plus gate at the output in the same manner as the A and B gates. Now this gate will be picked off the output from Q3353 down into the base of Q3367 to provide that pulse in the gating mode of the readout operation of the instrument. Now in at the base of Q3367 we have the positive going gate, but we're really interested in the negative excursion at the trailing edge. Okay, that negative step then is coupled through emitter follower Q3367, differentiated in C3368 and R3372. Now you might check your manual. That latter resistor goes to plus 15 volts, not to ground, as it shows on some schematics. Well, let's take a look at transistor Q3373. Now in the gated mode, the emitter is returned to ground. Another section of the switch connects the differentiating circuit. Now off the collector, over on the readout schematic, there's a 5.1K to plus 5 volts, which is the collector load. So initially Q3373 is on and saturated. Now that negative going differentiated pulse turns the transistor off momentarily. The collector goes up to 5 volts, and that is the trigger pulse that we need into the readout circuit to provide gated readout. Now in the free run mode, we just open the emitter and the collector goes to plus 5 volts, and that's the logic level which feeds over to the readout circuit to make the readout work on a timeshare basis rather than gated. All we have left on this diagram is the remote reset. Now you'll notice we have a pull up to plus 15 volts through R3391. There is a 15 volt charge therefore on C3391. So a ground closure at the remote reset input will couple a negative going step through that capacitor to provide the remote reset. And you'll notice just below, the Z-axis input just passes through this schematic. It also passes through schematic 2 and goes over to the Z-axis logic circuit. Let's turn next to the CRT and Z-axis circuit. That's found on pull-out schematic 14. To the right is the CRT. You may want to make a note of some of the voltages involved here. The post-accelerating anode sets at 21 kV, and the cathode at about minus 3 kV, so that means that we have an accelerating potential of 24 kV. The upper center portion of the diagram, Q4105, Q4115, and U4110 comprise the cathode regulator circuit. The lower left-hand corner is a CRT drive, the Z-axis amplifier, composed of Q4197, 4193, 4115, 4114, 4113. Now that's an operational amplifier which drives the CRT grid supply. Now all of the other transistors to the left are the Z-axis input and the logic circuits that determine how much Z-axis under certain conditions. Immediately to the right is the dynamic focus amplifier, Q4133, Q4137, Q4155. That's another op amp. Immediately above that amplifier, slightly to the right, is the dynamic focus DC restorer circuit, which generates the voltage that we'll use on the focus anode. It's composed of, well, CR4230, CR4231, CR4235, and CR4233. And just to the left, a similar configuration is the DC restorer, which supplies the grid bias voltage. And off to the left there, Q4250, Q4254 provides current to the graticule lights. Well, let's begin with the CRT cathode supply. Off to the left of the diagram there, T4201 receives the output from the inverter circuit. Now let's look at the secondary from the top there. At pin 7 we have about 3,000 volts peak to peak. And that's used in the times 14 multiplier to supply the post-accelerating anode voltage. And it also supplies a voltage doubler, which will be used for the cathode supply. Now that doubler is composed of C4205, CR4205, CR4206, C4206, and C4204. Okay, the output will be about 3 kV. The plus or reference side is tied to the output from the regulator circuit at the common collectors of Q4105 and Q4115. And the negative side goes directly to the cathode. Now just out of the voltage doubler are the filters composed of R4207, C4207, R4208, and C4208. Okay, let's follow that off to the right, and as I said before, goes down to the CRT cathode. It also goes into the error divider, which will be used in the regulator activity. That's composed, well, let's start at the top up there at plus 50 volts, the high voltage adjustment, and R4240, R4241, and that ties to the cathode supply. Then there's the focus bleeder, composed of R4243, the focus control, and R4242. Notice the asterisk beside some of those resistors, which identify them as part of a thick film pack. Then there's an additional 1 mil bleeder, composed of all of those 300K resistors, R4261, and all the rest of them to ground. Now off the error divider, at the bottom of R4240, we drive into pin 3 of differential amplifier U4110. Now that would be at 0 volts. Notice at pin 2, the minus input to that amplifier is referenced to ground. R4120 in series with pin 2 there is to provide an identical load as much as possible to that seen by pin 3, looking back into the error divider. All right, any error signal appears at pin 6, amplified and with no inversion, to drive into the base of Q4115. Now that's the output transistor. It has as its collector load the constant current supply, Q4105, in shunt with those two resistors to the left, R4101 and R4213. Well, let's look at Q4105. Notice its base is set by the divider, R4106 and R4108, so that we have a fixed voltage drop across the emitter resistor, which on my diagram is not labeled, providing a constant current into the transistor Q4115. Now remember that the output from this regulator circuit is the reference for the entire cathode supply, so that if we move the reference up and down, then certainly we move the output from the cathode supply up and down. Now let's see if we can get the regulator to work. Let's assume that the cathode has a larger current requirement. The cathode then would go less negative, or in a positive direction. The tap from the error divider then would go in a positive direction, as would pin 3 of U4110, and pin 6 would also go in a positive direction, which would bias Q4115 to greater conduction. The collector pulls down. Okay, the reference side of the cathode supply then is going more negative and would bring the cathode back down to where it was in the first place. And since we know that this is an operational amplifier, it would serve to maintain the cathode potential constant under varying current loads. There are several protective diodes in and around this regulator circuit. Now right at the input to the amplifier, CR4122 and CR4121 protect the IC from excursions in both directions. Now if we lost the cathode supply, that point would pull up toward 50 volt.
through the high voltage adjustment, and CR4121 would protect it in that direction. CR4122 would protect the IC in case you lost the plus 50 volt supply. You see at the top of the error divider. Now let's go to the output from this regulator and see what CR4101 will protect. Well, the output filter capacitor for the cathode supply, C4208, has about a 3,000 volt charge on it, plus on the top, minus on the bottom. And if the cathode supply is shorted to ground, you have a sizable positive going step coupled across that capacitor, which could do sizable damage to transistors Q4105 and Q4115. So CR4101 will clamp at 150 volts and protect those transistors. Now, before CR4101 comes into conduction, it will have lifted the collectors of those transistors. That step